This lesson deals with supplemental problem 219. You can find this problem in the ECE302 ebook in the Chapter 2 Supplemental Problems, starting on page 40. Let's simulate the quadrupler that we designed in supplemental problem 218 using 1N 4001 diodes, capacitors that are 0.47 microfarads, a square wave that goes between plus and minus 12, and a frequency of 5 kilohertz. And suppose we have a series current limiting resistor of 1 ohm. How many cycles do you need to run before you reach steady state? Verify the results of supplemental problem 218. What's the effective value of VD on? We need a square wave for our input. We can go back to what we learned about in ECE 201 and 202 about waveforms. I just pulled up that same information from those courses. We talked about a pulse, which can be turned into a square wave. Go from one level to another, and likewise back down again. Here's what I call V1 and V2. The pulse command starts with first level, second level. You can have a time delay before it repeats itself. There's a rise time and a fall time. There's a pulse width, and then there's a period where it repeats itself. We're talking about having a 5 kilohertz waveform, and so the reciprocal of that is 200 microseconds. If we want to have 200 data points, we'd have to have a print step that's around 1 microsecond in duration. Also, the rise time and fall time, if you recall, can be no smaller than the print step. Let's let the rise time and fall time be this 1 microsecond. It'll look like it's a perfect square wave. So you have to have a title and a dot end. I've got a pulse command, and my source node is labeled not a number but the letter S for source. I'm going to go from plus 12 volts to minus 12 volts. Have no time delay. Have a rise time and fall time of 1 microsecond. Period is 200 microseconds, and the halfway point is here if we start at 0. The rise time plus this would have to equal half of 200. Well, 99 plus 1 would be this rise time plus this pulse width. And then I have a current limiting resistance between the source node and what I label the in node of 1 ohm, and the diodes between 0 and A and B and C, C and D. The capacitors are between A and in, B and ground, C and in, D and ground. Our diodes can be the same that we had in our previous supplemental problem 2.5. I'm going to add in the breakdown voltage from the data sheet, which was 50 volts. I had to play with this, and I ran the simulation multiple times, but it took about 50 cycles to reach steady state. 50 times 200 microseconds would be 10 milliseconds. I'm going to leave this print step still at 1 microsecond because I want to have a fast rise time. So this looks like a perfect square wave. I'm going to start printing at time 0. And I'm going to pick the ceiling step to be the same as the print step to get a nice smooth simulation. Well, the results are on the next page. Let's take a look at that. Come back and talk about this last piece. Node voltage D, you can see here with a lot of steps, is eventually approaching 46 volts. Go back and see how that fits with our equations. I'm approaching 46 volts, and we were calculating that this should be 4 times Vmax minus VD on. We're using 12 volts for Vmax, and of course you have 4 here. This is approaching 46 volts, so I could solve for VD on. Take the 4, divide it into the 46, bring it on the other side of the equation, and then put this on the other side, and you get 46 over 4 minus plus 12, and that's a half a volt. And we'll see it's very consistent with our other waveforms on the next page, but what we're seeing is that in steady state, the current in the diode is getting smaller and smaller and smaller, and eventually it's sitting here at a value of voltage much less than 0.7. Let's take a look at the simulation output. First, I plotted node voltage A. Go back and look on page 39. That's the node voltage for the first clamp. You can see here it's going between a half a volt negative and 23.5. This is supposed to be approaching minus VD on. It's consistent with what we just calculated on page 40. And this is supposed to be approaching 2 Vmax minus VD on. Vmax was 12, 24 minus a half, or 23.5. So it's consistent with that. But it took quite a few cycles for it to reach steady state. Node voltage V is the first peak detector. And this is approaching 23 volts, and that would be 2 times 24 minus 2 times 1. That's consistent. And I plotted node voltage V sub C, and this is the second clamp, and we're expecting it to go at the bottom here to be 2 Vmax minus 3 VD on. That'd be 24 minus 3 times 0.5, and that's 22.5. And then the peak here is supposed to be 4 Vmax minus 3 VD on. 4 times 12, which would be 48, minus 3 times 0.5. is 46.5. And lastly, we saw V sub D before. Let's take a look at the capacitor voltages. First plot here is the voltage cross capacitor C1. That's between nodes A and N if you look back on page 39. And you can see that it's approaching 11.5 volts, and that's what we expect, because it's supposed to be Vmax minus VD on, so that was 12 volts minus 0.5 or 11.5. Note voltage B we had looked at before, and that's also the capacitor voltage, and we saw that that was approaching 23 volts, and that should be approaching 2 times the quantity Vmax minus VD on. 12 volts minus 0.5, so 11.5 times 2 is 23. Then the capacitor C3 is between nodes C and N on page 39, and you can hear it's approaching 34.5 volts. And if you take 12 volts minus 0.5 and multiply that by 3, that's 34.5. And then lastly, the voltage across node D is the voltage across the capacitor C4. And we'd seen before that that approached 46 volts, and that should be approaching 4 times the quantity Vmax minus VD on. 12 minus 0.5 times 4 is 46. And this is supplemental problem 219.